Okay, let's start off with some sample review board questions. Okay, so which of the following best represents power and time? So power equals work over time. So you can see they have an inverse relationship. It's not going to be a straight line because it doesn't look like it does in the formula. If it was straight, it'd be power equals 1 over time. So we know that they have an inverse relationship. So I have to just look up what an inverse relationship looks like. I go 1 over x. I'll look it up. And it looks like A is the closest one that matches that. Okay. So I'm talking about spring potential energy. So EPS equals 1/2 kx squared. So it does look like it does in the formula because those x's are squared, so that'll get us a straight line graph. Okay, and then the mass of the object used for this data is, so let's switch over screens here. So this is a EK versus, actually, yeah, this is an EK versus V squared graph. So we want to use this formula. EK is our y value, V squared is our x value. So our y value is already isolated. So y is EK, x is V squared. So our slope is going to be equal to everything else, which is 1/2 m. And if we want to find our mass, we move the 2 up there. So it's just going to be 2 times our slope. So 2 times 4.5 would be 9 kilograms as our answer. 9.00, whatever it wanted, however many digits it asked. And I would ask for digits in a numeric response question. Okay, so simple harmonic motion. So simple harmonic motion is kind of like this pendulum over here. Simple harmonic motion is just any simple repetitive motion. So it could be a pendulum, it could be a wave, it could be planets traveling around the sun, it could be a race car traveling around a track where it just sort of repeats over and over and over again. So there's some terms you need to know to do this. So period, which has a symbol big T. The period is the time to undergo one complete cycle. And you probably think of when periods, you think of girl periods, and that's because a girl period is the time it takes to complete one cycle of motion, so one ovulation cycle, so that's where it gets its name from. So doing a little bit of comm and physics in this lesson. So it can begin at any point and continues until that periodic motion begins to repeat itself, right? So if I go back to my pendulum here, and I wanted to time out one period, right? I'd have to start at the same point. So this would be where I start, and then this is where I finish. It's got to start and finish at the same spot, right? Same thing over here. So I'd start now and then stop, right? And if I time from the middle, I'd have to make sure that it was going to the right. So if I started now, this is when I'd stop, right? Hopefully my sound syncs up with my video so you're not like super confused from that. So it's measured in seconds. So a pendulum takes 4 seconds to swing from left to right. What's the period of this pendulum? So this took 4 seconds. Well, that motion isn't repeating itself yet, right? It needs to swing back and repeat the exact same thing. And it's going to take 4 seconds to swing back. So my period is 8 seconds. So frequency is the inverse of period. And what frequency measures is it measures the number of vibrations or cycles per second. Okay, so I'll explain this. So the base unit of frequency is hertz. And all that a hertz is just 1 over seconds, right? If period is seconds and we 1 over it, our units for frequency become 1 over seconds, but we just call it hertz. So to convert between frequency and period, you just have to use this formula here, which is under waves in your data book, but you just 1 over it. Okay. Okay, so I'll use this example to sort of explain what frequency is. So it takes a toy race car 4 seconds to go around a track. What is the frequency of the car in hertz? So here's my racetrack, right? And what it's saying is it's saying that's going to take 4 seconds. So this will take 1 second, this will take 1 second, this will take 1 second, and this will take 1 second. So if I'm talking about period, I want to know it takes 4 seconds to do 1 cycle, right? How many seconds it takes to do 1 cycle. But with frequency, I want to know how many cycles it can do in 1 second, right? So in 1 second, we only make it a quarter of the way through the track. So we could do 0.25 cycles per second. And you can see that if you took 4 seconds as your period and you went over it, you get 0.25, which is our frequency and is cycles per second. Okay, so with frequency, seconds are always on the bottom. With period, seconds are always on top. So amplitude is another term that comes up, and this is just how high or low something goes measured from the rest position. So if we're talking about the amplitude of a pendulum, right, it's just this height right here, right? So you might see that in questions with pendulums, is what is the amplitude, but it's just talking about that height. You can also do it with the spring. You can make a spring bob up and down. So the amplitude would just be, what is this height right here? That would be the amplitude. Okay, the frequency of a tuning fork is 440 hertz. It's called A440, so this is an A note. Determine the period of the tuning fork's vibration. So this one's really easy. If your frequency is 440 hertz and you want to find the period, you just went over it, right? And what 440 hertz means is it does 440 vibrations. It vibrates back and forth every second, so a lot of vibrations. So our period should be really small. So we want to know how long it takes to do 1 vibration. Well, if we go 1 over 440, we end up getting 0.00. We got 3 sig digs 227 seconds, and that's how long it takes to do 1 vibration. So that's our answer. Okay, what is the period and frequency of this in hertz on the tachometer? So tachometer tells you how many revolutions per minute or rotations per minute that your car does. And you can see that it's 9,000 because it times it by 1,000. So it's 9,000 revolutions or rotations per minute. So your tachometer is giving you a frequency because time is on the bottom. It's 9,000, we'll say, rotations per 1 minute. And anytime the time is on the bottom, it's a frequency. So if we want to know our frequency in hertz, we just have to switch this to seconds. And it's no different than converting between any other units. We put minutes up top to make it cancel out, and seconds on the bottom. So we get rotations per second, and that's a frequency. Right? So in 1 minute, there's 60 seconds. So I just have to take, oops, drop my calculator. So I just have to take 9,000 divided by 60, and I get 150 hertz. Okay, or rotations per second. And then to get this into a period, I just went over that 150, and I get 6.7 times 10 to the negative 3 seconds. And that's how long it takes to do 1 rotation. Okay, so that's my period, and this is my frequency. I'm going to get a new pen. Okay. There we go. So, what we're going to talk about a pendulum, and I want to know what affects the period of a pendulum. And usually I do this as an actual demonstration with a real pendulum, but of course this makes it harder. So what I have here is I have a pendulum simulation. We're going to use this for our lab in a bit, right? So our pendulum swings side to side, and the nice thing we can do is turn friction off, right? If we have friction, and this was what would happen in real life, is it would end up stopping eventually, but when we turn friction off, we don't have to worry about that, and it'll just swing forever and ever and ever. So I can time the period of this pendulum, and I want to know, what can I do to change that period? Okay, so what do you think I can manipulate? So one thing that we can manipulate is our string length. So we can have a long string, and we can have a short string. And then that's what we're manipulating, and we're trying to find out what will affect our period. How will it affect our period? Okay, our responding is actually going to be period the whole time, and I don't want to write this out with my mouse, but our period is what we're looking to affect. Okay, other things I can change from that simulation is I can change my mass. I can make my mass big, or I can make it small. That's something that I can change. So we can have a big mass, and we can have a small mass. Right? And another thing that we can change is we can change our amplitude. So I can stop this. I can have a big amplitude, or I can have a small amplitude. So I'm going to try changing that. So big amplitude, small amplitude. Okay, and normally we can't change gravity because I do it in real life, but in this simulation you can change gravity. So maybe we can add gravity here. I don't know. We can manipulate gravity in this, but normal situations on Earth you can't. So our period is always our responding variable. We're trying to find out what can affect our period, and things we want to control are the other ones that we're testing, right? So if we're trying to change our string length, we want to keep our mass and our amplitude controlled. If we're changing our mass, we want to keep our string length and amplitude controlled, and if we're manipulating our amplitude, we want to keep our mass and our length controlled. Okay, so we're going to see what actually affects our period, right? So what we can do is we can start out with our control one. So let's make it 30 degrees, and let's make our string length, let's do it halfway. Sorry, I should stop it. And then our mass, we'll put it halfway. Sure, this will be our controlled experiment, where we have it at 30, like that. And you can see that our period is 1.44. Okay, so first thing I'm going to do is I'm going to adjust my string length. So let's make it longer and see if that affects it. Okay, so I want to make sure I reset it every time. I want to bring it back to 30, and then yeah, so you can see that that had a big impact on our period. It made it quite a bit bigger. So it looks like they have some sort of direct relationship because it made it bigger. If I put it back at 0.5, put this back at 30, make sure to control that, right? Here's at 1.44, so that's our control one, is 1.44. So it looks like the string length did affect it. So we'll do the mass next. So 1.44 is our control. So if I make my mass quite a bit bigger, but keep everything else the same, and time it. It looks like we got 1.44. So surprisingly, mass doesn't affect it. And normally we would think that mass would affect it, but it does not. Mass doesn't affect it, right? And then let's test our amplitude. So let's increase our amplitude. Let's just increase it to 40 here. So it looked like it increased it, it changed it a little bit, but not to the degree that our other one did. And if I just make it, let's make it 10 degrees. Right, it's still around that 1.44, so it has a little effect on it, but not really. And it has to do with the fact that this is approximated as a perfect circle, and it's not, but it doesn't have that big of an effect on it. So amplitude doesn't make a big enough difference that we actually include it in the things that affect it. It's basically around 1.44 each time. And just because we can, let's change our gravity. Let's see if that affects it. Oh yeah, so gravity, when we increased our gravity, it made our period a lot smaller. So it looks like they have an inverse, some sort of inverse relationship, because that changed it quite a bit. It was a significant change. Okay, so our string length affected it quite a bit. Our mass had no effect. Our amplitude had a little effect, but it wasn't big enough. And gravity had a big effect, right? So now we can take a look at our formula. So our formula for the period of a simple pendulum, we use this. And look, the two things that affected it are on there. Length affected it, gravity affected it is on there. When we increased our G, we saw our period went down. That's why they have an inverse relationship. And when we increased our length, we found that our period increased as well because they have a direct relationship. It's a square root direct relationship, but you get the idea. So period is T. L is length of our string, and G is our acceleration due to gravity. So what is the expected length of a pendulum with a period of 1 second? Oops. So let's do that. Okay. So let's see how we would use this formula. So period equals 2 pi square root L over G. That's an L. I use a handwriting L so it doesn't look like a 1. So we're trying to find this length here. So to find that L, because it's square rooted, you gotta square everything, and we get T squared equals 4 pi squared L over G. So when you square everything, T squared, the 2 squared becomes 4, pi squared becomes pi squared, but these guys are unaffected because they were square rooted. So we want to find our length, so we move G up top and 4 pi squared down below. And we can assume this takes place on Earth, so 9.81 meters per second squared. Our period is 1 second squared, all divided by 4 pi squared. So make sure you use your pi button in your calculator. So 9.81 times 1 squared divided by 4 pi button squared. And we get our length to be 0.248 meters. And lots of times on a test, it'll be 24.8 centimeters. Most of our lengths for pendulums are in centimeters, so that's how you're going to see it. Okay. Yeah, so pretty straightforward. So I have a board question here, so we'll watch this video. There won't be any sound, but this is what can the second girl do to help herself look a little less foolish? Okay, so let's get rid of my pen and let's watch the video. So this is the expectation. And this is reality.
God. Too slow.
Okay, so take a second to think to yourself, what could she change about her experiment in order to do better, right? So pause the video, you can think about it for a sec, and try to figure out what the answer would be. So we have our formula. Okay, so changing amplitude and changing mass, if that was your answer, those wouldn't have an effect on her period, right? She wants that period is too quick for her. The time it takes for it to swing back and forth is too quick. She can't get up. So what we want to do is increase that period. So there's only two ways and really one reasonable way to increase that period. Because L and T have a direct relationship, if she finds a swing with a longer string, then she's going to get a longer time to be able to do it. And that's probably what the girl in the first video is doing. Right, her other option, which is less reasonable, is lower G. So if she went to the moon and did this, then she would have more time. But that's also complicated because as she jumps, she'd sort of jump up and down slower, but she'd probably be able to time it better. The best answer is increase the length of that string, right? Increase the length of her pendulum, and then she would do better. Okay. So I was going to do both lessons today, but they're kind of long doing them together. Let's do this board question first, and then after this board question, I'll show you what homework you can do, and we're going to call it a day, just because I don't want like an hour lesson for you to have to watch. So I'm going to break it up into 2 segments, and I'll post the other one tomorrow. So if a pendulum has a frequency of 3 Hertz on Earth, what would the period on Titan, which is 4 times Earth's gravity? So try this out, see if you can do it, and I will go through it right now. So there's 2 ways to do this question. There's an easy way and a hard way. And the easy way to do this is those numbers without numbers sort of questions. So this is our formula, and you have to think about what we're changing. So what would be the period on Titan, which has 4 times Earth's gravity? So the easy way to do this is the only thing that we're changing. It's the same pendulum, 2 pi. We're changing our G, right? So the changes we're not making any changes to the top, and on the bottom, we're changing it by square root 4, right? Because the G is square rooted, so the 4 has to get square rooted. So we just take our period and we multiply it by 1 over square root 4. Right? And obviously square root 4. Square root 4 is 2. So it would be half of what it would be. But they give us the frequency on Earth. So the frequency on Earth is 1 Hertz. So you got a 1 over that, and then multiply it by 1/2. So 1 over 3 times 1/2, and you get 0.16 repeated seconds. That's what the period would be on Titan. Right. The other way of doing this question, the much harder way, is you have to find common ground in between them. So you get period equals 2 pi square root L over G. L is the same between Titan and Titan and Earth. So if you find the length on Earth, because you know this on Earth, you know this, find the length on Earth, and so rearrange this, and then use that same length to do another question. And now you know the length on Titan. You know this is 4 times on Titan. You know 2 and pi, so you can find out that on Titan. But the other way is much easier, much quicker, less steps, and you'll still get the same answer, 1.6 repeated as your answer. Okay, so the homework you can do, we'll do all this tomorrow, is you can do all this here, right? So it's not too much. A few questions, this period and frequency stuff is pretty easy, and then you can do all the pendulum stuff. There's some standard of excellence questions. So give those a go, and let me know if you have any questions. Hey everybody, so we're gonna do the second half of this lesson. So we did pendulums yesterday, and we're gonna do springs today. So we need to talk about the things that we can manipulate with the spring. So springs are a little bit more confusing because we've seen pendulums, but what I'm talking about with the spring is something like, oh, it's in slow motion. It's something like this, where we just move it up and down. So how can we change the period of that spring? And you can see some things around here are things that we can change. So just brainstorming things that we could change is we could have a large mass, and we could have a small mass, right? And for all these respondings, it's all our period. That's what we're trying to change. Is we're trying to find out how can we change our period? What can we manipulate, right? So other things that we can change is a spring constant. So we can have a large spring constant. We can have a small spring constant, right? And then we can also have a large amplitude, and we can have a small amplitude. Okay, and then because I normally do this in real life, we can't change gravity, but something we can manipulate is gravity as well, right? We can have a large gravity, small gravity. So we're just going to go through and we're going to see what actually affects our period, what we can manipulate to change our period. So I'm just going to stop this. So we're going to have a control one, and this one's a little bit trickier because we don't have a period timer, we just have a stopwatch. So a way you can always improve your accuracy when timing things is you can time more than one, and then there's going to be less error in that. So we want to turn our dampening down. So this is going to be our control one, and this is what we're going to compare it to. So we have a 100-gram mass. We have a spring constant that is on the third tick here. And then we have, so we can get out a ruler here, and we always want to measure our displacement from our equilibrium position. So this shows the mass equilibrium, and if I put on a heavier mass, you can see that it changes at equilibrium point. So we always want to make sure that our measurements, our amplitude, how far we pull it down, is always from that equilibrium point there. And we'll start off with Earth gravity, and let's pull it down 20 centimeters for an amplitude. Okay, and then I'm going to time out a few of them, and I can turn it in slow motion to help. So I'm going to bring it down. Oops. Sorry, so we're measuring from the middle there. So I want to measure 20 from about the middle there. So that looks like that's going to be our amplitude. And since I turn the dampening down, it'll just bounce like this forever and ever. So I can turn it into slow motion now. And I'm going to turn this period trace on to help us. So it always starts the period as soon as it goes there. And I'm going to measure 2 of them just to increase our accuracy. So I'm going to start it. And I'm just going to do one more. Oh, I think I screwed up there because it doesn't record it every time. Sorry, let's try that one more time. So let's start it. So this is 1 period, and then this is 2 periods. So it's annoying that it does it like that, where it sort of leaves out half of it. See, it leaves it out this part, and then it starts over again as it's going up. Sorry, I've never used this before, so I'm just noticing. Yeah, and then it leaves out half of it, and then it starts it again going down. That's super weird. But for 2 periods, it was 1.63. Maybe I'm going to leave out that period trace for the future. So we're going to stop it. Okay, so the first thing that we said that we can manipulate is our mass. So let's increase our mass quite a bit. We'll stop it, and you can see that equilibrium point has changed. So we had 1.63 as our That's going to be our 2 periods. So we're going to measure again. We're going to make our amplitude the same. Okay, and I'm going to reset it. So I'll start it when it goes back to going to, there we go, start it there. It goes back up, so that's 1 period. Oops, sorry, I lost track of this. Let's start this again. So I'm gonna start it when it's going down. Sorry, this is a bad video so far. Killing you guys' time. Okay, here we go. Start. Okay. And then when it's going back down past that equilibrium point, that's 1 period. Okay. So now we're at 1 period, and we'll have to measure 1 more. There we go. So you can see that it increased it quite a bit, by about a second. So, so when we had the large mass, we got an increase of the period. So bigger mass, bigger period. So it looks like they have some sort of direct relationship. So the mass definitely affected it. So let's see if spring constant has an effect on it as well. So we'll go back to our control and we'll stop it. So now we're going to change. Let's have a big spring constant, so that changes our equilibrium point. We'll reset this. We'll pull it down to 20, and then we'll start it when it's on the way down. So we'll start it now. So that's 1. That's 2. And you can see, so our control one was 1.63, and it looks like changing the spring constant did have an effect on it, but when we did a larger spring constant, we have a smaller time. So it looks like they have some sort of inverse relationship. So if we go back here, the largest spring constant decreased it. Oops, decreased it. But it did have an effect on it. Okay, so let's test out our amplitude now that we got everything going good. So we'll go back to our control, which is there, and 100 gram mass. So let's do a bigger amplitude. Let's do an amplitude of 40. Let's double it. And I'll start it there. So that's 1. That's 2. So we got 1.62, our control was 1.63. So it looks like amplitude has no effect, just like with the pendulum. So definitely amplitude, no effect, no changing to that responding, right? And then we can try out gravity here. So let's go back to our control and let's just boost up gravity there. Oops. Doesn't let me go down any further, so we'll go 20, but we'll do it down here. So this will be 20 right there. Okay. So everything else is controlled. Okay, and we'll start it there. So that's 1. And that's 2. So 1.64, 1.63 is our control. So it looks like gravity actually has no effect on the amplitude, or sorry, the period of it. So gravity doesn't affect it. So it looks like only the mass and the spring constant. And sorry, I didn't talk about these controls. So right when we did our control group, when we were trying to change things, when we were trying to change our mass, we kept our amplitude the same. We kept our spring constant the same. We kept our gravity the same, right? You want to control these other things that you think will affect it, because if you don't know what's really affecting your experiment. So we kept mass the same. We kept amplitude the same. We kept gravity the same. For this one, we kept mass the same. We kept spring constant the same. We kept gravity the same, right? So you want to control those other ones, and you're only manipulating one thing at a time. So if we look at the formula, we said that mass had a direct relationship, spring constant had an inverse relationship, and look at that, it's true. It's got one of those square root relationships as well, but mass and period are direct square root, and then period and spring constant are inverse square root. Okay, so T is our period, M is our mass, and K is our spring constant. Okay, so that formula can be found under waves. Here, let me show you. Let me find a formula sheet. I'm looking for a physics 20. There's one. And get this on here. So if you want to find those, they're found under waves right here. So we have the first one is the spring constant one, the springs, and then the second one is the pendulum one. So you have to know which one is which. Okay, so the math is pretty much the same. A spring vibrates with a period of 0.81 seconds. When a 300 gram mass is attached, calculate the spring constant. Okay, so we're going to use period equals 2 pi square root m over k, and the mass is 300 grams. It's got to be in kilograms. Oh, sorry, we're trying to calculate our spring constant, so we have to rearrange it. So we'd have to square everything. So we get t squared equals 4 pi squared m over k, right? The squared and the square root would all cancel out, and then we move our spring constant up top and our t squared down below, and that's what we get. So 4 pi squared, our mass is 0.3 kilograms, and then our time, our period, is 0.81 seconds, and that has to be squared. So we do that. I'll show you how to type this in to the calculator. Just give it a second to open up here. You guys are my first video of the day. Here we go. So if I was typing this in, the way that I would type it in is I'd do my top in brackets, and usually when I do 4 pi squared, we're going to do that a lot in the next little bit. I just do it all together. I don't need any multiply signs by that, and then I multiply that by 0.3 kilograms, so that's my top, and then my bottom is 0.81 squared, like that, and then that would be my spring constant, 18 newtons per meter. Okay. Okay, so this is a board question, so you can pause the video after I ask the question. So we have the same situation, but just to make it a little bit easier, we have this spring oscillating, and this is a frictionless floor, and it just oscillates back and forth, and this shows the equilibrium position. So if I go back to this here, let's put gravity back to Earth's gravity so it doesn't look weird. There we go, Earth's gravity here, and we'll just do it in normal motion. So this line here is on the other one as well. That represents our equilibrium position, right? So actually, let's slow it down. So this is position 1, this is position 3, and this is position 2, right? So this is what's happening. It's just oscillating back and forth like that, right? So if we go back to our image here, so here it's going through the equilibrium. This is when the spring is stretched out as far as it can go. It comes back to position 1, and then it's stretched in as far as it can go. And it's always nice and symmetrical. This amplitude here, they're always going to be the same. They're not always the same, but in physics we make things easy and we make them always the same. So those amplitudes are the same. So this is maximum expansion, maximum compression, and this is in the equilibrium position, right? So if you want to find the maximum velocity, which position would it be at? So pause the video, take a second. It's always better to think about these yourself because I will give the answer in 1 second. But think about it, pause the video, see if you can figure out and see if you can get it right. Okay. So we can see when it's at its maximum compression and maximum expansion, switching directions, right? So for whenever you switch directions, you have to stop for a brief instant. So at these two positions, it stopped and it stopped. So the only one it's actually moving through is that equilibrium position. So my equilibrium position is going to be my fastest, and then 2 and 3 is going to be my slowest. Okay, so pause the video, see if you can figure out this. Where's the maximum kinetic energy? Where's the minimum kinetic energy? Okay, so our formula for kinetic energy is EK equals 1/2 mv squared, right? The mass doesn't change. So the bigger the velocity, the bigger the kinetic energy. So it's going to be the same. The maximum kinetic energy is where it's moving, and the minimum kinetic energy is where it's stopped. Try this one, maximum spring force, and see if you can do it. Pause the video. Okay, so our spring force, remember this formula, is Kx. Right. And as we're doing this experiment, the spring constant doesn't change, right? That's one of our controlled variables. The spring constant is staying the same. But what is changing is that distance x, that displacement, right? So amplitude is what we call it, but we also called it x before. That's our displacement from our equilibrium position. So the bigger the x is, the bigger the spring force is, right? So here, we're at our equilibrium position, we have no x, so there's no spring force as it's moving through there. So my minimum is going to be 1, but my biggest is going to be when it's stretched out the furthest, right? That's when the spring wants to bring it back to that equilibrium position. So 2 and 3 is going to be the answer for that. Okay. And then maximum potential energy and minimum potential energy. So pause it, see if you can figure it out. Okay, so we're not talking about gravitational because it stays at the floor level the whole time. We're talking about spring potential energy. If we go back to this, what I can do is I can turn on this graph. Let's get rid of this ruler here. And we have, you can see kinetic energy, potential energy, gravitational. I wish I could put it on the side because it's a little bit less to look at. Oh, I can't change my height being 0. That's annoying. It's just too much to look at. So this is elastic potential energy here. So you can see that, yeah, I don't like these. I'm not going to look at it this way. Sorry. So EPS, it's too confusing when it's vertical like that. EPS equals 1/2 kx squared. Right? So here we're at the equilibrium, we have no x, so our minimum spring potential energy is going to be at 1. But when we have these compressions and expansions like this, it's going to have the most spring potential energy. So 2 and 3 are going to be the biggest because they're the only ones with x. Okay. So hopefully that went okay, and if you have any questions about it, just shoot me an email and I can help you out with that. Okay, and our last question of the day, these are going to pop up more now that we have these graphing skills. So find the spring constant from the graph. Okay. So what we need to do is we have period squared here and mass. So we need a formula with period and mass and spring constant in it. Okay, that's what we need. So obviously we're going to use period equals 2 pi square root m over k. So that's what we need. And we also need the slope of this graph, because that's what we're doing right now is we're doing slopes. So this is going to be my point 1. And then my point 2, let's make it right here. This is going to be my point number 2. Okay. So what I'm going to do is I'm going to find the slope using those 2 points. And I just need to write down what those 2 points are before I switch to my other screen. So we're going to use y2 minus y1 over x2 minus x1. So y2 looks to be, so you have to be careful with this. You have to figure out what each one of these represents. And there's, I think they represent 5. So 2, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Yeah, it looks like it represents 5. So my top point's going to be 205 for y, and the units are seconds squared. And then my bottom one's going to be 50 seconds squared. And then my x, so these ones look like they go up by 2s, 92, 94, 96, 98, 100. So this is going to be 92, 94, 96. So 96 kilograms, and then my other one's going to be 10 kilograms. Sorry, I just had to write that down because I can't see the screen anymore when I switch screens. Okay, so we can find our slope. So 205 minus 50 divided by 96 minus 10. So our slope is equal to 1.8023, and our units would be seconds squared per kilogram. So that's our slope. So now we need to use that new skill that we learned earlier this week to use that slope to turn it into a spring constant, right? So our formula is t equals 2 pi square root m over k. But our graph was t squared, so period squared, versus mass, which it doesn't look like that. So what we have to do is we have to make sure this is in proper y equals mx plus b. We have to make sure they look like they do. So if I square everything, and I end up with t squared equals 4 pi squared m over k. Let's continue that line like that now. The original formula, this and this are the same thing. If you square everything, it's the exact same thing, right? But now it looks a little bit more like our graph, right? We have to get this in y equals mx form, we have to make sure that our y value is isolated. It is isolated. Okay, there's our x, there's nothing added on, so it's just y equals mx. So our y value is period squared. Our x value is mass. So what this tells us is that our slope is equal to 4 pi squared over k. It's everything else that I didn't circle there. So we have our slope, right? We found it. We have 4, we have pi squared, so we can find our spring constant. So our spring constant is going to be equal to 4 pi squared over slope. So all I have to do is I have to take 4 pi squared, and then I have to divide it by 1.8023 seconds squared per kilogram. And I get I have room down here. Yeah, I get 21.9. Okay, so I want to talk about the units. So I'm just going to erase this here, and I'm going to talk about the units. So we know the units normally for a spring constant are newtons per meter. What we would get over here, because we have nothing on top, and on the bottom we have seconds squared per kilograms, right? Those kilograms can just move up to the top, because 1 over kilograms is just moving them up to the top. We could put our units as kilograms per second squared, right? But I thought it equaled a newton per meter. Well, let's take a look at this. Let's break a newton down. So F equals MA. So a newton is equal to a kilogram meter per second squared. So instead of writing a newton, I can write a kilogram meter per second squared. Right? And now meters and meters cancel out. Look at that. They equal the same thing. A kilogram per second squared and a newton per meter, the same thing. So you could put this 21.9 kilograms per second squared, or you could put 21.9 newtons per meter, and both mean the same thing. Both would be acceptable answers. Okay, so you're going to see questions like that on your test, your next test coming up, so make sure you practice that. Okay, so hopefully you've done this stuff before, so this is added on to it, and give it a go. And if you have any questions, shoot me an email, and I would be more than happy to help you. Okay, so thanks. Thanks for watching.